Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. We have been discussing the quantum mechanical solution of hydrogen atom. Today we will discuss one particular aspect of hydrogen atom problem that we have so far ignored. That is, when we wrote down the Hamiltonian of this hydrogen atom, we said that we have this nucleus and an electron, and the electron is orbiting around the nucleus. So, therefore, we wrote down the kinetic energy of the electron and the potential energy of the electron, which potential energy of the attraction between electron and the nucleus. But what we have ignored in our formulation is that there exists an inherent or intrinsic property of electron which is not yet considered in our discussion. That is, electron has a spin. This spin is inherent to the nature of electron. You cannot separate spin from an electron. If there is an electron, electron has its spin, so spin is always present. So, therefore, there is a flaw in the discussion that we had, and we will try to correct it to some extent in today's class. One thing that you must keep in mind is that spin has the spin of electron that we are discussing has no classical analog. So, here is a new system that we are a new property that we are going to discuss, which does not have any classical analog, but we would provide a quantum mechanical formulation for this. It was first discovered by the experiment in the experiment by Uhlenbeck and Goudsmit in 1925, when they observed splitting in the D line of sodium spectrum. This was the first experimental observation, but the explanation of it could be obtained by a Stern-Gerlach experiment, where an atom was subjected to magnetic field and then its effect was analyzed. To explain that, I am going to take help of an animation which is found in the internet. So, I would simply go to this website whose address is there in the slide. I would show you this quick animation. You see, suppose I have applied a magnetic field, and now I am sending a bar magnet with a particular orientation through this magnetic field. When this tiny bar magnet goes through the field, it gets deflected based on the orientation of this dipole, and then if I monitor this, I would see that it would be deflected to different extent based on the orientation of the initial orientation of this tiny magnet. Now, you would see, if I do this experiment many times, I would see that all possible orientations are observed. On the other hand, if I send, instead of a bar magnet, if I send a quantum mechanical magnet, that means an electron which has got a spin, I would see that instead of having this continuous distribution of orientation, I have only two different orientations possible. These two different orientations, popularly we call them as alpha spin and beta spin. In this case, what we see is that this electron behaved like a quantum magnet. So, this video is designed and realized, and the credits are being shown here. I gratefully acknowledge the contribution of these people in making this beautiful animation, which gives a nice insight about the Stern-Gerlach experiment. As I mentioned, the link to this video is shown here. So, to summarize, what we saw is that if we send electrons which behave like quantum magnets, we would actually have only two orientations, whereas a classical prediction would have said that all possible orientations are allowed. So, this is what we would try to express in terms of the quantum mechanical formulation. So, what we have seen is that that electron has got this spin, and the spin of this electron can be expressed through the so called spin angular momentum. The nice thing about it is that the spin angular momentum of this electron follows all the angular momentum commutation relations that we have discussed during our discussion on the angular momentum. So, for example, if you remember the Lx, Ly, which are the x and y component of the angular momentum operator, they did not commute with each other. So, similarly, this now S is replacing the L. L is the general definition of the angular momentum, and now I am considering S, which is the spin angular momentum, and one can show that the x and y component of the spin angular momentum, they do not commute with each other. In fact, Sx, Sy, Sz, they do not commute with each other, whereas there exists this operator S square, which commutes with Sx, Sy or Sz. So, again similar to our discussion with angular momentum operator, we now have this special case where I cannot simultaneously define the Sx, Sy, Sz, whereas I can define S square and one of these three components of S vector operator. And analogous to what we did, we are now defining S square and Sz are the two operators for which we are constructing the common eigenfunctions. So, the eigenfunctions for these operators are still given by the same spherical harmonics. Only thing is that what are the values of S and Ms. We have different particles which have got different spins. For example, electrons have this spin is of 1/2. Well, on the other hand, the protons also have spin of half. Photons have got S of 1, spin of 1, and pions have S equals 0. So, different subatomic particles have different spin. They are this spin angular momentum of these particles are their inherent nature, their character. This is how they are. We know this by doing experiments. For example, when I talk about the electrons, I saw that when I subject them to a magnetic field, external magnetic field, I see only two different orientations. When I have two different orientations, that means I know there are two different states. So, from our earlier discussion, we said we knew that when for a given value of S, my Ms value would be from minus S to plus S in the step of 1. So, I wrote this expression in terms of L and ML, but now I am defining them in terms of S and Ms. So, here for example, since I would see, therefore, how many states should I see? So, I would see Ys Ms, the number of states that I can see are 2 Ms plus 1. Since in the case of electron I see only 2 states, therefore, Ms must be half, and that would see that my S when I define my S value as half, then I would be able to describe this. So, these two different orientations show that we have two different states. And how can we have two different angular momentum states? We know that if we have angular momentum S, corresponding to that I have Ms value going from minus S to plus S in the step of 1. So, therefore, if I have angular momentum as S, I have 2S plus 1 number of Ms values. So, therefore, Ys Ms, the number of such functions are given by 2S plus 1. And since in the experiments that we discussed, I have got two orientations or two different states. So, therefore, this shows that S or the spin of electron is half. When spin of electron is half, what are the spin states? So, I have Ms going from minus S to plus S. So, therefore, I have one state as y half minus half, another function is y half plus half. Please note that these two functions have same value of S but they have different values of ms or the magnetic orientation. So, these two functions are popularly known as alpha spin or beta spin or up spin or down spin. As I said, these are pure quantum mechanical functions, they have got no classical analog. Now, let us see what are the expectation value for this alpha spin and beta spin. Since these are the same spherical harmonic function that we discussed in angular momentum, when I apply s square operator on this function, the eigenvalues would come out to be s into s plus 1 multiplied by h bar square. When I apply sz operator on this function, I get ms multiplied by h bar as the eigenvalue. So, in other words, if I apply s square operator on alpha spin, I would get s is half. So, this is 3 half into 1 half, that is 3 by 4 h bar square alpha spin. So, alpha spin actually represents the state of that electron. So, s square when I apply on beta spin, I again get. So, both alpha and beta are eigenfunctions of s square operator. They are also eigenfunctions of sz operator. When I apply sz operator on alpha, I get ms into h bar. Ms I call for alpha spin as plus half. So, this is h bar by 2 alpha. When I get apply sz on beta electrons, I get minus h bar by 2 beta. So, both alpha and beta electron are simultaneous eigenfunctions of s square operator and sz operator. Now, what has happened is that we have defined our electronic wave function psi n l m as a function of r, theta and phi. This function we described as in terms of radial function, which depended on n and l as a function of r, and then the angular function which depended on l and m, which quantum numbers, and the functions were theta and phi. So, this is our hydrogen atoms eigenfunctions that we have defined, and using these eigenfunctions we are actually describing the state of the electron. So, you already know that we have different energy levels, and corresponding to one energy level, corresponding to energy levels depended on only n, whereas the wave functions have dependence on n, l and m, and for an energy level corresponding to principal quantum number n, we had n square number of states defined. But in all those definitions we had ignored the electron spin. So, now to describe the total final or the complete state of the system or the complete state of the electron in this hydrogen atom, this is not adequate, because we have left something, and that is the electron spin. So, now my new wave function that I should have not only dependence on n, l, m, which will have r, theta, phi, but I also should be introducing my y, s, m, s. What is this coming? These are the spin functions of the electron, and since electron have spin as half. So, I am writing this y half and ms. How many functions are there of this kind? There are 2. So, therefore, each orbital here psi n l m will now be having 2 different manifestations based on their electron spin. So, I can have now psi n l m ms r theta phi, maybe I would introduce omega as the spin coordinate. So, I have these 3 at the space coordinate, and this one is the spin coordinate. So, for since there are two possible values of ms, so therefore, I will have now each psi n l m will be splitted to psi n l m alpha, psi n l m beta. So, these are now the two functions, the two eigenfunctions that define the state of the electron completely. So, if you remember, for energy corresponding to principal quantum number n, we had n square number of psi n l m. This for n equals 1, we had only 1, for n equals 2, we had 4 different functions. Now, we see that since each state function, the special function can be split into two, one corresponding to alpha spin, another corresponding to beta spin. So, this gives me as 2 n square degeneracy, and this 2 n square degeneracy takes into account the effect of the electron spin. So, when I describe this wave function, this is not a mere orbital, this I actually call as spin orbital. The spin orbital, so these and these are called spin orbital, and these are called normal plane orbital, which mean that I am talking about only the spatial coordinate, so space. So, popularly we call this orbital, that is why one orbital could hold 2 electrons, one with upspin, another with a downspin. That is because the wave function corresponding to an spatial orbital has 2 spin orbitals in it. Now, we will continue our discussion, because what we have seen now is that we have electron which is going around the nucleus. So, therefore, it develops an orbital angular momentum, and then we have got this spin which is also an angular momentum. Now, we have got 2 angular momenta in our system. So, what is the consequence of that we will discuss. For example, when the electron goes around the nucleus, we develop the magnetic dipole moment that we described as minus E divided by 2 m E L, where L is the orbital angular momentum of this electron, E is the charge of the electron, and m is the mass of the electron, and this minus sign is coming because of the charge of electron, which is minus E. So, this is the orbital magnetic dipole moment that gets generated because the electron is moving. But since now we have the electron which has a spin, I would also expect another dipole moment which will be spin dipole moment that will be present in my system. How would I write that? I will write something very similar way, E divided by 2 m E, and instead of L vector I write spin. So, S, this corresponds to the spin angular momentum, but there exists another term over here, we call this G, or the this is called anomalous spin factor, which is equal to 2 for 1s orbital of hydrogen atom. Its values would actually keep on changing for different angular momentum. So, this depends on the angular momentum of the electron, but this anomalous spin factor is present in this case. We will not be able to derive this quantity, this G in this expression, because this has got purely quantum mechanical origin, and Dirac's method of relativistic quantum mechanics obtains this value of G from ab initio, but for our discussion we will just introduce that we have this term over here. So, now I see this hydrogen atom that I have, which has a simple one nucleus and an electron. I see that the fact that the electron goes around the nucleus, it develops a orbital dipole moment, and since electron has a spin, it has a spin angular momentum. Now, these two dipole moments, they interact with each other. So, this angular momentum and this angular momentum L and S, they couple with each other. So, we have got orbital angular momentum and the spin of electron, so and they couple. So, when they couple, without this coupling, I had the Hamiltonian of the system, the kinetic energy of the electron, the potential energy of between the electron and the nucleus. Now, this was the Hamiltonian that we discussed. Now, because we have this orbital angular momentum and spin angular momentum and then they are interacting with each other. So, we have this L dot S as the new term, which is called the spin orbit coupling. Spin orbit coupling. So, this is the new potential energy operator that is appearing in my Hamiltonian. So, this is often given with a multiplied by a constant which is called the spin orbit constant. So, this spin orbit constant it would be a function of the internal coordinate. It would also depend on the principal quantum number of the states and so on. So, this is now my new Hamiltonian. So, the point that we would now discuss is that if I did not have this term and I had only these two terms in my Hamiltonian, in that case the Hamiltonian would have commuted with the angular momentum operator. We know that is because we have used this the function as the total wave function as the radial and angular function, because we saw the Laplacian has this operator Laplacian has a Legendrian term and that has a fixed value or definite value of L. So, therefore, the Hamiltonian would commute with L operator. Since Hamiltonian did not talk about the spin at all, so therefore, in this case the Hamiltonian would be commuting with spin, because the Hamiltonian did not have any term which depended on the spin variable. So, therefore, they would be two independent variables, so they would anyway commute. But now, when I have this term added into the Hamiltonian, so this commutation does not hold. So, what is the consequence of it? When H and L or H and S, the Hamiltonian or the spin or the orbital angular momentum, they commute, then I can express the eigenfunctions of this Hamiltonian operator in fixed value of orbital angular momentum or with a fixed value of spin. But when they do not commute, there is a problem. The problem is that the total eigenfunctions that I would have for this new Hamiltonian, which has now the spin orbit term, would not have a definite value of an orbital angular momentum, nor would it have a definite value of spin angular momentum. So, that is a problem for us. Luckily for us, what happens is that we can show with some algebra that even if L and S they do not commute with the Hamiltonian, what would commute is a new angular momentum that we call L plus S. We define that as a new operator J. This can be shown that the addition of two angular momenta also gives you an angular momentum. So, we define this L plus S as a new J angular momentum, where this J angular momentum would commute with the Hamiltonian when the spin orbit coupling is introduced in my problem. So, now since J angular momentum commutes with the Hamiltonian, so the eigenfunctions of this Hamiltonian would not have a fixed value of L or would not have a fixed value of S, rather would have some fixed value corresponding to this J angular momentum. And since J is an angular momentum operator, so I can always define its eigenfunction as y j m j, where j square, if I apply on this, I would get j into j plus 1 h bar square y j m j, and if I use j z on y j m j, I will get m j h bar. So, this is the beauty of angular momentum operator, because if I define that this is an angular momentum operator, I have readily available solution for these angular momentum operators. So, now I see that these functions yj mj are going to be the eigenfunctions of the Hamiltonian and not ylm or yss. ylm or ysms, they are not going to be eigenfunctions of this Hamiltonian where spin orbit coupling is introduced, rather this yj mj are going to be the eigenfunction of this Hamiltonian. Now, the point is that how do I define this j and mj? This is what we would do now here. So, if I have defined j as L plus s, so the quantum number j would go from L plus s to L minus s mod, and of course, mj value will go from minus j to plus j in the step of 1. So, therefore, I have 2j plus 1 number of mj level and j value. So, let us see when L equals 0, what are the values of j. For spin of electron, since we are considering electron, so s is half. So, the j values are 0 plus half to 0 minus half, mod of 0 minus half. So, therefore, j is only one value of, and that is half. When j is half, what are the mj values? So, mj values are plus and minus half. So, what are the final functions? Y half plus minus half. So, these are the new eigenfunctions of my the Hamiltonian of hydrogen atom when I have spin orbit coupling introduced. So, for L equals 0, I am getting two functions, half plus half, half minus half, where these are expressed in terms of j. Now, let us do it for L equals 1. When L equals 1, s is anyway spin of electron. So, that is half all the time. So, I can have 1 plus half is 3 half, 1 minus half is 1 half. So, these are the two different values of j that is available. So, corresponding to j equals 3 half, I have 2j plus 1 number of mj values, they are plus minus 3 half and plus minus half, and for j equals half, I have 2j plus 1, that will be 2 number of mj values, and these are the values. So, how many functions I define here? I define y, j, mj, since I define 6 number of functions, y 3 half. So, what are these functions? Y 3 half plus minus 3 half, y 3 half plus minus half, and y 1 half plus minus 1 half. So, I have now 6 number of functions for L equals 1. Similarly, for L equals 2, you would see that j can have 5 half or j can have 3 half, and then in that case you would see that number of y j m j would be 10, because m j values would be plus minus 5 half, plus minus 3 half, plus minus 1 half, and in this case we have plus minus 3 half, plus minus 1 half. So, I have 10. So, please see, when L equals 2, this is d orbital. When L equals 1, this is p orbital. When L equals 0, this is s orbital. How many functions can I describe in terms of for s orbital? There are 2. What are they? When I have s orbital, I write in this way. So, this electron is defined by, each electron is defined by one of these spin states. In case of p orbital, I have now placed for 6 electrons. 3 of them will have 3 different spatial orbitals, and for each spatial orbital we can have 2 different orientations. So, these are the 6 functions that I have for p, and similarly for d orbital I can have 10 number of electrons which are given here. So, in this way, when we incorporate spin orbit coupling into the Hamiltonian that we have discussed, we can see that we are obtaining the complete identity of the electron in our hydrogen atom problem. Thank you for your attention.